Hello guys, nice to see you. How was your long weekend?
Good morning, teacher.
Hi,
How are you?
good, thanks. How are you guys?
Very well.
Everything is good.
Fine.
Nice. Hi.
Good morning.
Things are going, everything is fine. Already involved in studying process. Set it up. No issues. Okay, so if there are no questions, let us continue with our discussions. And at this point, after considering already motion in two dimensions and introducing the parameters which can describe this motion, we make a next step in our course. So initially, as I mentioned at the beginning, we focus on purely on kinematics, which main task is to predict the position of any body in space over some time interval based on the known information about its initial position, also its velocity and acceleration vectors. And the main task is to eventually get the position vector as a function of time. However, in the scope of kinematics, we never ask a question which is the reason for this motion. And next topic we will discuss, like chapter of general physics and mechanics in particularly, is dynamics. So dynamics will specifically be focused on understanding the reasons of motion, means some forces, which is force is some vector quantity which possess some magnitude, and also definitely its orientation as a vector plays a big role, because it really depends how it will change the conditions of the motion of the body based on its orientation and magnitude. So in order to make these first steps into dynamics and proceed further, we need to introduce three laws of motion, or they're sometimes also called Newton's laws. So that will be pretty much main part of our discussion for today. There are three laws of motion. We will go step by step, discuss in details each of them in order to understand the concept behind them. And afterwards, probably already next lecture on Friday, we will proceed with some applications, some examples of applications of these laws of motion under different conditions. Okay, so let me change the camera. And first of all, we need to define several things. So these laws of motion, they were not derived from any models. So these are purely empirical laws, which were obtained only because of repeating observations of processes which are happening around us. Based on this fact, it becomes quite natural to predict that these laws of motions, they have some limited frame of applicability. And first of all, these laws are not applicable for bodies which move with very high speed, because their laws of relativistic mechanics work. Means very high speed is like something close to speed of light. Also, it doesn't work for very small objects, like close to atomic or subatomic particles. Those are also governed by laws in the scope of quantum mechanics. So Newton's laws, or laws of motion, how we understand them in classical mechanics, they are applicable for quite everyday life experience in terms of mechanical processes. And that we need to understand, so that there are some limits of applications. So let us start with the first one. And we can formulate it as follows. So in the inertial frame of reference, we will talk about this definition of inertial frame of reference a bit more just after this introduction of the first law of motion, but in few words, just a system of reference which does not move with any acceleration with respect to the body which motion is studied. So it should be either stationary or moving with constant velocity with respect to the body the motion of which we try to describe. But we will talk about this in more details shortly. So in the inertial frame of reference, a free or quasi-free body does not experience any acceleration. So what does mean free or quasi-free? Free means there are no forces acting on this body. Any forces don't act on this body. And quasi-free, it's the case when there are a bunch of different forces acting on the body, but they act in this way that the resultant force is equal to zero. So they compensate each other. So in general, we can write that if the sum of all forces is equal to zero, which comes more realistic in real world, because absolutely free body, it's really very difficult to achieve, actually quite impossible. But to realize a situation when all forces compensate each other, that's another story. So when the sum of all forces is equal to zero, so here we put vector, then the velocity of this body should be equal either to zero or some constant value. So means its acceleration should be equal to zero. So this is pretty much the formulation of the first law of motion. Means that in order to get change of velocity of the body, there should be some net resulting force acting on it. If this motion is studied in the frame, inertial frame of reference. So let us consider two frames of references. One will be, let's say, stationary, and we can consider it as some inertial frame of reference, doesn't move at all. So it will be X, Y. And another frame of reference X prime and Y prime. So this, the origin of the second frame of reference can be given, like its position can be defined by some position vector R naught. Means with respect to the origin of this stationary system frame of reference. Then let us assume that the second frame of reference is moving with some velocity, a constant velocity V naught. This is constant. Now we have some body, some point body A, which is moving with its velocity V prime and acceleration A prime. And that is with respect to the second frame of reference, and its position of this point A is defined by position vector R prime with respect to the origin of the second frame of reference. So under these conditions, we can already see here that we can also define position of this point A with some position vector with respect to the origin of the first frame of reference. So it will be some vector R, which is nothing else as the sum of two vectors. First, it's R naught, position of the origin of the second mobile frame of reference, and position vector of the point A with respect to the origin of the second mobile frame of reference, R prime. Okay, so now we define this position vector R, and we can go from position vectors to velocity vectors. For that, we need to take first derivative over time from all of these vectors. So let us write it here. dr over dt is equal to dr naught vector over dt plus dr prime vector over dt. So now we have this equation for derivatives, and we know that first derivative of the reduced vector is velocity. So velocity, like total velocity of the body with respect to stationary system of coordinates, v will be equal to v naught. It's this derivative delta r naught over delta t, which is constant velocity of second frame of reference with respect to the first one, plus v prime, which is the velocity of the body with respect to the second frame of reference. So now we make one more step and go from velocity vectors to acceleration vectors. And in order to do that, we need, again, take first derivative of these velocity vectors over time. So dv over dt is equal to dv naught over dt plus dv prime over dt. Here, we need to take into account the fact that according to our condition, initial, this v naught vector is constant. So it doesn't change over time. If it doesn't change over time, means that this derivative will be equal to 0. So from here, we can write that total acceleration of the body with respect to stationary frame of reference is equal to a prime vector, which is acceleration of the body with respect to the mobile second frame of reference. So we see that for velocity, it changes because v is equal to v naught plus v prime. But for acceleration, it doesn't change. A is equal a prime. So we can claim that velocity in this condition is variable, like variant, some variable parameter, and acceleration is invariant, so not variable parameter. So since acceleration doesn't change when we go from one system of frame of reference to another frame of reference, means that our mobile frame of reference, the second x prime y prime, is inertial frame of reference, and this satisfies this condition because v naught is constant vector. So if from going from one inertial frame of reference to another frame of reference, we see that acceleration remains invariant, that means that the second frame of reference is also inertial. So it's necessary to underline that like truly inertial frame of reference is kind of idealistic concept because that's quite challenging to realize. For instance, our planet Earth is not ideal for building any inertial frame of references attached to it because our planet, first, it spins about its own axis. That's the reason for changing the day and night. And also it rotates, like performs some revolutions around the sun. So we have one revolution per year. So both of these motions result in some centripetal accelerations. And when we study motion of bodies in the frame of reference related to planet Earth, that of course will exert certain limitations in terms of considering it as true inertial system of reference. So by the way, this motion around the sun. So do you know what is the impact of this motion on our climate on Earth? Have any ideas? Because the fact that it spins about its own axis, it changes day and night. And then there is another effect originated from rotating around about the sun.
This is because we have like winds.
Well, winds we have because of different pressure in atmosphere, and that is the reason of sun, like energy we get from the sun in form of radiation. But let's say we can rephrase this question. What is the reason for change of seasons? Exactly. But there is one moment which could be specified because some people claim that seasons are changing because Earth is coming closer and further from the sun because our orbit is elliptic. But that's not true. Our orbit of the Earth is quite close to a circle. It doesn't change the distance. And the reason for changing the seasons is actually related to the orientation of its own axis of spinning about its own axis. So the orientation of this own axis about which Earth is spinning is tilted at 23 point something degrees. And the fact that it's tilted and it moves around the sun on a close to circular orbit actually eventually results in the fact that the northern hemisphere, for instance, has summer and the southern has winter, and vice versa. So that just some deviation from topic, but I believe would be good to remind. Okay, so at this point we defined quite clearly the first law of motion. I've shown conditions for inertial system of defining an inertial system of a frame of reference, and we can proceed further. So let us go to second law of motion. And this law of motion quite often in textbooks is defined as follows. So there is some force is equal to m times a mass times acceleration. However, to be more precise, this second law of motion should be written in a bit different way. So acceleration is equal to force divided by mass, because acceleration is the result of acting force on the body. So that would be more appropriate way to define it. And of course, we need to keep in mind that this force F is considered to be as some net force, like sum of all forces applied to the body. So here we have direct relationship between applied force, acceleration, resultant acceleration, and there is some coefficient which relates them, and this is the mass. It would be good to define now what kind of mass it is, because there are two types of mass. It happens that they are equal, but from pure physical point of view, there are two types of mass. First is gravitational mass, which defines the weight. So it's mass times g, is free acceleration or free fall. So this is gravitational mass, and it actually defines how, like quantifies how this property, which is called gravitational mass, of this feature of the body interacts with the gravitational field. Another type of mass is so-called inertial mass, and this is actually this mass which is included into the equation which defines the second law of motion. And it just tells how this mass, it quantifies how much body resists to change of its velocity upon the action of a force. And you can feel already that it's kind of, from the physical point of view, quite different processes are happening. Gravitational mass is interaction, quantifies interaction with gravitational field, and inertial mass quantifies interaction with some force, like which is exerted on the body. However, it happens that these two types of masses, they are equal to each other. So let us, since we in this particular case are dealing with inertial mass, let us try to figure out what is the right way to measure this inertial mass. Any ideas? Or maybe not. So you can keep thinking about this, but probably makes sense first to define how we measure acceleration. And then we go to mass. It was a bit too in a rush to start from measuring the mass. Okay, acceleration. So how would you measure acceleration from your perception and experience?
Delta V. Velocity.
Can you repeat, please?
Like V minus VO, V0.
Okay, so
Change of velocity.
that, let's say acceleration is constant, and then we want to have change in the velocity, like in the, let's say, speed. Let's consider one-dimensional motion. Let's say V2 minus V1, change in the speed, and then what we divide by, what should be in the denominator?
Time.
Difference, like time interval, for during which this change of velocity happens. Also T2 minus T1. Yeah, it's the way to go. So you can measure velocity or speed at one moment of time, then repeat this measurement in the some other moment of time. You have the difference in speed, difference in time. You can get some either acceleration if it's constant or some average acceleration. And if you technically can manage to push this time interval close to zero, approaching to zero, then you can measure at any moment of time, like instantaneous acceleration. So idealistically, it's something like that. Okay, with this, it's quite straightforward. Now we still have this task to measure the mass, inertial mass. So any ideas with measuring the mass? So probably you do this quite often. We use some scale and we measure the mass. Is it applicable to our task or not?
Yes, why not?
Well,
Like
from
the
quantitative,
equation defines the mass. You're asking this?
no, I mean, it's not an equation which defines the mass. It could be maybe, I don't know, density multiply volume. It's not about that. It's the concept how you would measure the mass. Because, so you ask if there is any difference. And there is a difference. So from quantitative point of view, there will be no difference because gravitational mass and inertial mass, they are equal. But from the physical point of view, since they have different physical nature, it was also required that you find appropriate approach to address gravitational mass, like measurement of gravitational mass, and inertial mass. So what we do when we use scale, we compare weight of reference body and some unknown, like body with unknown gravitational mass, because weight is defined by interaction of gravitational mass with the strength of gravitational field, which is J, acceleration of free fall. But that is gravitational mass. And here we want to define inertial mass. So for this purpose, we want to go somewhere far from any planet object in space, just empty space. There are no any like forces acting on the body. And let's say we have a string attached to some body with mass m1. And m1 is our reference. We know this mass. We have some system of units in which we measure. We need to have some reference for this system of units. So imagine that we have this reference. And then no force is acting besides one. Let's say we just pull this body with some force F. We can measure force with some known force F. Then we let it go back, so it moves a bit. And when we stop exerting this force F and let this system spring and mass move in the original equilibrium condition, it will start to move with certain acceleration, A. And let's call it A1. So we know that we can measure acceleration. It's quite clear how we would measure this. So we have some reference mass, we have known force, and we get some acceleration, A1, which we can measure. Good. So we measured it, and now we can attach to the same string another object with mass m2, which is unknown. We apply, so it stays in the equilibrium, nothing acts on it. We apply the same force F as in the first experiment. It is shifted from equilibrium condition, then we let it go back to equilibrium condition, and this mass will move with some acceleration A2, which will be different from A1, because mass 2 is different from mass 1. We also can measure this acceleration A2, And then when we finish all these like 2 experiments, we can write according to the second law of motion, we can write that A1 is equal to our force divided by M1, mass of the first body. Then A2 is equal to our force divided by M2. And from here, if we define F from each of these equations, and it's the same force, so we can put sign equal between the expressions for F from left and right side, we will get that M1 divided by so A1 is equal to M2 divided by A2. And from here, we can get that M2, which is unknown, is equal to M1 divided by A1 times A2. So if we measure the acceleration A1 with the reference body, then yeah, actually you are right. It was messed up. So it should be not like this. We expressed F and I was confused. So the ratio between the mass M1, so let's write it here. M1 times A1 is equal to M2 A2, yeah. And then we can write that M1 divided by M2 is equal to A2 divided by A1. Okay. And from here, we can express M2. So if we know M1, we can measure A1, we can measure A2, and we can then determine M2. In the scope of this experiment, we will be able to determine correctly from physical point of view, address the determination of unknown inertial mass of the body. So this is the way how we could correctly approach this measurement. And this is important because it's not that we just define second law of motion with this equation and just accept it as it is. We also need to discuss the physical concept behind each of these parameters. So, and the best way to do it is to discuss the process of correct measurement of this parameter, truly understand what it is, even if these parameters are so trivial from first point of view as just mass and acceleration, which seems that we actually already know everything about it, but still some detailed discussion is important. By the way, any ideas how modern accelerometers work, which are some miniature accelerometers which are embedded in your smartphones, for instance? Because usually you don't do these measurements, you don't measure speed time difference and get acceleration, you want to get your acceleration immediately and preferably in 3 dimensions. So you want to have ax, ay, and az. And there are devices, they called accelerometers. They measure accelerations in different directions. So the most common one is based on some piezo. Well, could be an option, but so you could maybe attach it to geolocation and see how it changes over time. Could be an approach, but usually it's designed in a separate device, which is a piezoelectric accelerometer. That is something like this. Let's say we have some cube for 1 dimension. We have some piezo crystal. So piezo crystal is some crystalline body, some single crystal, which produces some voltage at its edges. So here we have some voltmeter. When we compress or stretch it. So here is some metal sphere, could be quite small, but with known mass, which is attached with some string. And under normal conditions, let's say when it doesn't move, it pushes this piezoelectric crystal with some force. So that results in some voltage which it generates. And for instance, when we start to move it with some acceleration left or right, it either releases this crystal or presses even more. And that causes in change of the voltage, which can be detected with some microprocessor, analyzed, and when it's done repeatedly for calibration, you can find the relationship between the generated voltage with this piezo crystal with acceleration with which this system is moving. So if you have 3 of these arranged in perpendicular directions, you can address accelerations in each ax, ay, and az. So it means you have total information about the acceleration. So since you can make such devices quite small, and they will be probably the most accurate in terms of measuring acceleration. Okay, so let us move to the last law of motion, the third one. And that one tells us that there is some reaction when we put some force on the body. There is some reaction force, which is oriented in the opposite direction and is equal by magnitude. So we can write it as follows. It will be force from first body on the second, F12, is equal to minus force which is exerted by second body on the first. And graphically, we can show it like this. Let's say body, one body, so it's 1, this is 2. Then we have some force F 1, 2, which body 1 exerts on body 2, and there is another force which is the same in magnitude but different in opposite in orientation, as F2, 1, exerted by body 2 on body 1. So that is important to take into account because that will define the conditions of like stationary condition when, for instance, we have some body on the table, and obviously we know that there is some weight of this body, m times g. It pointed downwards, and since there is some force, it should move with some acceleration because it has some mass m. However, nothing happens, so it stays in stationary position, and that is because this weight is compensated by so-called reaction of the surface on which this body resides, and it's denoted as capital N, or could be just N, so it's oriented in the opposite direction, and under stationary condition, when it doesn't move neither up nor down, what actually happens with bodies which we put on the table or other surface, we can write that mg is equal to minus n vector. So we have some gravitational force, like weight of the body, which is compensated by the reaction of the surface on which this body is located, and nothing is happening in terms of motion. Okay, I think that with this we introduced 3 laws of motion with some discussion of each of it, and our next step will be to discuss applications of laws of motion in like during our lecture on Friday. So if you have any questions, you are welcome. If not, we will consider this continuation of this topic under some, in the form of some examples on Friday. Okay, change to the camera. Then thank you very much for your attention. Have a good day and take care. Hope to see you on Friday. Bye-bye.
Thank you. Goodbye.
Thank you.
Thank you.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.